We have now released issue 3 of the New Thinking Aloud magazine. Download it for free at newthinkingaloud.org. New Thinking Aloud is a non-profit endeavor. Your contributions to the New Thinking Aloud Foundation make a meaningful difference in our ability to produce new videos.
Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Today we'll be exploring zero-point energy and the potential for literally transforming humanity by harvesting this resource. My guest is Professor Garret Moddel, Emeritus Professor of Photonics and Quantum Engineering at the University of Colorado. He is the author of more than 200 scientific papers. Garret is based in the Denver, Boulder area of Colorado, not far from me, actually, in Albuquerque. And now I'll switch over to the internet video. Welcome, Garret. It's a pleasure to be with you today.
Thank you. I'm delighted to be here.
And welcome to New Thinking Aloud. This is our first interview, so it's a double pleasure for me.
Thank you.
We're going to be talking about zero-point energy, and I know it's a phrase that is commonly heard these days in the culture, but my best guess is that probably 50% of our audience won't know exactly what zero-point energy is. So why don't we begin by defining it?
So zero-point energy is a strange phenomenon that was developed. The concept was developed in the early 20th century, first by Planck and then by the people who furthered quantum mechanics. And the idea is that, and it ultimately comes from the uncertainty principle, which says that you cannot measure two linked parameters to absolute precision at the same time. So, for example, you can't measure the position and the velocity of a particle to absolute precision at the same time. So if the particle were standing completely still, then that would mean that you did know everything about it. The end result is that nothing can stand still. So everything wiggles. All stuff wiggles. Everything's got this ground state energy that wiggles. And not only does stuff wiggle, but space itself does too, in the sense that there are always electromagnetic oscillations, electromagnetic fluctuations that come in and out of existence throughout all space. And so this strange phenomenon has been the ground state in quantum mechanics, but it's generally considered to be a ground state that's just there. You can't really take away from it or give to it except for a very short period of time. You just borrow and so on. It's just there.
You know, it reminds me of a thought that's been around esoteric literature for a long time, that the universe itself is alive.
Mm-hmm. Okay. I thought you were going to go in a different direction. So yes, it is conceptually that everything wiggles, everything is alive. I thought you were going to go into a discussion of the void and nothingness, and that everything emanates out of nothingness, and that also ties in with zero-point energy and the vacuum.
Because things are constantly moving in and out of the void. Is that what you're saying?
Yes.
And so as an engineer, your interest is this energy. If we were to try and quantify it, it could add up to something quite significant.
It's a huge amount of energy that's there. If one does the calculation, it turns out to be absurdly high. In a cubic centimeter of volume, there's enough energy to boil all the oceans. But the question is, can you ever access it? Can you ever remove it?
And this, of course, has been the quest of inventors, I should imagine, for many generations. The idea of what would you call it? I know you have technical terms for it, but there are the notion that you can get something out of nothing. In effect, has always defied inventions up until now. I mean, maybe the atomic bomb is something of an example along those lines.
It has been around for a while, and it's been fodder for inventors and quacks.
Yeah.
And the problem is, often one speaks about free energy systems. So that is systems which get energy indefinitely out of nowhere, and you just continue to obtain as much energy as you want. And at least all the physics that I'm aware of just does not agree with that. Energy must come from somewhere. It doesn't just exist. It just doesn't keep on coming from nowhere. And so I believe often this is a misunderstanding of zero-point energy. Even zero-point energy presumably has to come from somewhere, perhaps the space itself.
People might, if they have a religious orientation, say it comes from God.
Fair enough.
But in other words, we are not able to pinpoint the source other than to say, as you did earlier, the void.
Right. It exists. It's a fixture of nature.
And I know from our previous discussions that in order to tap into this energy or to harvest it, one would need to apparently violate the second law of thermodynamics. So let's talk about that.
Okay, so the second law of thermodynamics has a lot of different variations in how it's described. But one way of looking at it is that you can't have a system that's at a uniform temperature, so say ambient space all around us, and continuously extract energy from that. You need a temperature difference to drive the energy flow. And if, in fact, with zero-point energy, you're extracting it from the thermal background, from just ambient space, then yes, it would violate the second law. But it's not clear that that's where zero-point energy is coming from. In fact, there's been some recent work just in the last, actually a little more than a decade theoretically, and in the last few months experimentally, that discusses quantum energy transport. So according to this, just as one can transport information, say in a quantum computer, from one place to another through nothingness, one can transport energy via the same mechanism. And if you can do this, that means that when we're extracting zero-point energy from one location, it's actually being transported in from somewhere else. So you're not violating any law. So it's just unknown at this point.
You're talking about what people have called the quantum leap, where a particle, an electron, might move from one orbit to another orbit without passing through the intervening space?
It is related to that, yes. It's tunneling, which is essentially a quantum mechanical tunneling is, as you say, getting from one place to another without ever having been in between.
And so this is a well-established principle in quantum physics.
Yes, it is.
So what you're suggesting, and if I understand it correctly, you've built many, many devices that are able to, at least at a very small scale, harvest energy in this fashion.
My lab has been building quantum tunneling devices for decades, just not for zero-point energy.
We've also, in our previous discussions leading up to this interview, talked about the importance of the Casimir cavity. And I know this is central to your own interest in harvesting zero-point energy. So once again, we need to define it for our viewers.
Good. So in 1948, Hendrik Casimir thought of this concept. He developed this concept in which you have two closely spaced mirrors or metal plates. And he derived some equations for this, showing that these two plates that were closely spaced would be attracted to each other, even if they have no electromagnetic attraction or anything. And he was trying to figure out what it was and spoke to really the grandfather of quantum mechanics, Niels Bohr. And there's a famous story about how they went for a walk together, and Niels Bohr, in his usual way, sort of chatted about all sorts of stuff that Casimir didn't understand, and then said, 0-point energy. So Casimir thought, so what this concept has been developed into is that in all free space, there are these electromagnetic modes of all frequencies of 0-point energy. And these are moving everywhere all the time. If you have two closely spaced mirrors, then those mirrors restrict the electromagnetic modes or the light modes that are allowed inside. You're only allowed to have an integer number of half wavelengths. That is, you can have a wave that goes to zero at the two plates because it's a half wavelength, or you can have it be a full wavelength or 3 half wavelengths, but it can only be a restricted number of wavelengths. Whereas outside, in free space, you can have all of these electromagnetic wavelengths. So the interpretation then is that what's happening in a Casimir cavity is you've got a restricted number of wavelengths. Outside, you've got all the wavelengths. So there's radiation pressure pushing from the outside plates that's not being matched inside. The net effect is that you get a pressure that pushes the two plates together, and they go together. And so Casimir proposed this in 1948, and then in the late 20th century, it was verified to increasing accuracy experimentally. And so this actually works.
In other words, it would be a way to create some kind of a differential in the background 0-point energies, like an energy sink of some sort that might enable you to harvest the difference between these spaces.
I agree with the first 3/4 of what you said. So yes, it's an energy differential between inside and outside. Now, can you harvest it? And this has been the concept that a number of different inventors have played with. Well, yes, those two plates do get pulled together, and yes, you can harvest it, but only once. It's a little bit like holding a brick, and you say, okay, the force of gravity is attracting this brick. I'm going to let it drop and extract the energy. Yes, you can do that once, but then if you lift the brick back up, you've used just as much energy as you've gotten, and so you haven't gained anything. In physics, it's termed a conservative force. You don't get more out than you put in. And that's also true for Casimir plates. You don't, if you let the force attract the plates together, yes, you'll get energy out, but you won't be able to do it continuously.
Well, I understand. We were talking earlier, and of course, I'm sure our viewers know I have no background in theoretical physics or experimental physics or electrical engineering, the fields in which you're an expert. But my understanding is that you've built devices that employ the Casimir cavity in a situation where there's also quantum tunneling going on. And that enables you, and in fact, as you point out, over 1,000 different experiments to harvest the 0-point energy.
Yes. And the way we do it is by having fixed Casimir plates. We're not moving the plates. And we have fixed Casimir plates, and we take advantage of the fact that the 0-point energy density inside this Casimir cavity is lower than it is outside. Then directly adjacent to these Casimir cavity devices, we have another device, an electron tunneling device. And the concept that I think is working here, we haven't proved that this is how it works. The concept I think is working here is that because of the energy density difference in the Casimir cavity and outside, we're driving energy across these two, across the quantum tunneling device into the Casimir cavity. So we're using the Casimir cavity to create an asymmetry in the 0-point energy density, and that's what gets us energy out of the system.
Because if I understand it correctly, normally the quantum tunneling devices that you use would be in equilibrium. Electrons would be tunneling equally in both directions through the device.
Yes.
But the Casimir cavity is at one end of the device, and so that creates the imbalance.
Exactly. I think there's another element that's required. And again, we haven't proven this, but our experiments are consistent with it. And that is that, as I mentioned earlier, the 0-point energy from a quantum mechanical point of view comes out of the uncertainty principle. And the uncertainty principle can be stated a number of different ways. One of the ways is that the uncertainty in time times the uncertainty in energy of a particular particle cannot be zero. That means either you've got to have some fuzzy time or a particle existing for a time that it shouldn't, or you've got to have a lot of energy for a very short time. And it turns out that for the energies that we believe we're tapping, which correspond to red light, the energy of red light, the uncertainty principle says that these fluctuations can exist for roughly a femtosecond. So that's 0.015 zeros 1 seconds, a very, very short time. And so the idea is that, and there's some good theory supporting this, that you can borrow the energy from the vacuum for a femtosecond, and then you've got to give it back. In our device, what we're doing is they operate extremely fast. This tunneling mechanism is femtosecond fast. So I'm thinking that what we're doing is we are essentially borrowing the energy from the vacuum for a femtosecond, capturing it, and then not giving it back. So we're bilking the vacuum of its energy.
Now, I understand you've been doing these experiments actually for a couple of decades. And is that correct?
Well, we've been doing tunneling experiments for a couple of decades. The current device that we're working on is something that I invented about 3 years ago. And so we've really only been working on this for about 3 years and refining the technology.
One of the major things, of course, that you have to do is look at every possible alternative explanation that might be something conventional, like, some sort of flaw in the system itself.
Yes. So we've done, for the first 2 years, we spent as much time trying to disprove ourselves as to prove that what we were getting was in fact correct. So we thought it might be due to some sort of electromagnetic pickup. We thought it might be due to a chemical reaction in our device, and that our device was actually some sort of fuel which was decaying and giving us energy. And So we looked into a lot of different alternative possibilities. And as far as we can tell, none of them panned out. In other words, it looks like this is not an artifact. It looks like it really is energy extraction.
And I gather your devices are very small, but they have potential for being scaled up and actually providing useful amounts of energy for all sorts of practical purposes.
I believe so. So our devices right now, the ones we're making are usually on the order of 1/millionth of a meter, a micron, in size. So one edge and another edge. And we've made some that are 10 times that, but they're still tiny, tiny devices. And so the amount of energy that we're getting out is tiny. But in principle, it should be scalable. So we should be able to, with the proper technology, link these devices together into an array of zillions of devices and get as much energy as you could out of a, say, solar panel of the same size. The difference being that a solar panel needs to be fed by sunlight, whereas this would give power indefinitely with no apparent source. It would be the quantum vacuum.
Well, I can well imagine that all sorts of financial interests would be interested in scaling up and seeing if it would work.
Yes and no. They would if they fully believed it. Because what we're doing is very different and against the grain, we're having trouble getting traction. I've published so far 3 papers on this, one in a very mainstream journal, the Physical Review Research, and they've gotten very few citations, virtually none. I mean, fewer than a dozen, which means that people say, okay, this group at the University of Colorado thinks it's tapping the vacuum energy. I'm not sure. I believe it. And so the venture capital community and the rest of the industry also is very skeptical at this point.
Well, and I gather that this skepticism is to a large degree related to the enormous influence of the second law of thermodynamics, which suggests that what you're endeavoring to do is impossible.
Yes, what you say is correct, but I'm not even sure that we are challenging the second law. At first, I thought we were, but the more I'm working with this, the more I'm of the opinion that we're not violating any laws here.
You found a workaround, essentially.
Found a workaround.
But the question is, since so many people over so many decades have endeavored to come up with a similar workaround and have all failed, the implication must be in the minds of most conventional reviewers that this is obviously yet another failure.
Yes. In fact, I early on contacted a colleague of mine who's a very sharp guy and nice guy. He's a Nobel Prize laureate, and he has worked with the quantum vacuum in his own work. And he was very patient listening to me. And finally, after a discussion back and forth for a few weeks, he said, "Garret, I can't find any flaw in what you've done, but I just can't believe that this works." He said, the smart money is against you. Many people have tried to do this sort of extraction and have failed. Chances are you're wrong. And I appreciated his honesty.
And I would imagine if someone came to you with a similar device, you might have a similar attitude.
People do, and I do. I hope I'm a little more open-minded just from the wounds that I've received, and so that I do, to the extent that my time and knowledge allows, investigate what people suggest and try to take a look and see if it in fact works. And I've been in a number of discussions online with inventors of various sorts of technologies and exchanged ideas and suggested experiments for them.
What we're getting into, I suppose, has a lot to do with the philosophy and the sociology of science. That is, when you come up with a finding that seems to go against existing thought patterns about how these things should work, how does the scientific community adjust to these things? And I would imagine, to be conservative, it just takes a lot of time.
It takes a lot of time. As we are taught in the book, The Structure of Scientific Revolution by
Thomas Kuhn.
We have a particular paradigm, and we have a particular perspective. And as new information comes in, we fit it to that perspective. We fit it to that paradigm as much as possible. If there's contradictory information, we're skeptical and we sort of put it aside until that contradictory information becomes so overwhelming that we then go through a shift, and that's a scientific revolution. That's at least the way that, in principle, it should work, or at least is described to work. Unfortunately, scientists are people, and people believe in what they believe in. And the Church of Science is fairly rigid, and it progresses very slowly, and perhaps too slowly.
The last major revolution in physics, the quantum physics and general relativity, are now both over a century.
Yes. There are various sorts of anomalies that don't quite fit what we've seen and what quantum mechanics and relativity and our cosmological views would tell us. And so but usually these things are folded into the current explanation. So for example, and this is not my field, so I'm going a little far afield here, but in cosmology, there's the notion of the Big Bang, that the universe was formed from a singularity that expanded very quickly and eventually built into our current universe. But there's a real problem between the initial timescale of the Big Bang itself and the current universe. And so there's been a patchwork that's been put in place to try to accommodate it, called inflation. And even cosmologists who support the Big Bang theory, many of them say that, inflation is a little bit artificial and it's got some problems in it. And so if we look at a number of these theories, there are patchworks. Now, of course, we've got the patchwork of dark energy and dark matter, which we know must exist if our current model is correct, but we don't know what they are. And so there are holes all over the place here that are eventually going to accumulate, and eventually, I assume, will give rise to another revolution. But we're not there yet.
Well, my understanding is you've looked for about 8 or 9 alternative sources for the energy output of your devices. You've been able to rule those out, but I imagine a creative thinker would say, well, sometime down the road, in the future, we'll come up with some additional hypotheses that will explain in a more conventional way the findings that you've now been reporting.
Yes, that is certainly quite possible. And therefore, I think that the way that we have to proceed at this point is not trying to prove that our tiny devices are putting out what we expect they're putting out according to the theory as we understand it, but instead we need to scale up. Mm-hmm. If we can build a little widget the size of this stapler, and have something that just puts out power continuously, that'll run a little motor or drive a light bulb, and there's no sources of input that can be measured. At that point, I think we've proven it beyond a doubt.
Now, I do understand from some of our earlier conversations that from a technical point of view, there are a lot of problems in doing this in terms of contamination that might occur.
So that has to do with the fact that we're working out of a university lab. In the last few years during which we've been developing this project, we have had two major floods where my lab was ground zero for a burst pipe in the ceiling. And so that destroyed everything, and we had to sort of close down for a while. We've got constant power outages. We've got contamination everywhere. The university, in its wisdom, decided to put a Wi-Fi hub right in the ceiling above our sensitive our sensitive measurement apparatus, so that we're getting constant interference now. And so it really is a problem of dealing with the sorts of issues we've got at a university lab. I think once we are able to set this up in an external lab or a company that is used to working with semiconductor device technology, I think the scale-up will be fairly rapid.
I can imagine for some big corporation with billions and billions of dollars, what you're suggesting, and of course I'm only guessing, but it might be a few $1 million to put together this stapler-sized device that you're considering.
Yes, I mean, if Intel decided to work on it, or Apple or somebody like that, they've got the resources to set it up very quickly.
And naturally, it could be done in a room which is shielded from all sorts of external sources of contamination.
Yes. The semiconductor processing that is now currently being used to make the chips that go, for example, into our cell phones is incredible in terms of the degree that contamination is excluded, and also the precision of the devices that are made. Devices in current semiconductor technology are being made at the nanometer scale. So a nanometer is roughly 5 interatomic distances. So devices are being made that are 10 or 20 interatomic distances in size. Layers are being made that are just a couple of the interatomic distances. And these are being done reproducibly enough that you have transistors in your cell phone that number in the billions, and they all work. So the industry is incredible. I mean, however amazing you think that semiconductor technology is, it's 100 times more amazing once you actually get into what's being done, and the quality of work that's being done, which incidentally is why it's so hard for the United States to restart its semiconductor fabrication technology, because it's so damn sophisticated.
Well, where I live in Albuquerque, I know Intel has a big factory, so they must have invested surely well over $1 billion simply in that facility. Now, an interesting thing about zero-point energy from my perspective as a parapsychologist is one of the most important papers in the field was developed by Harold Puthoff working with Bernard H. These individuals are known to have been involved in parapsychology, and if I recall correctly, Arthur C. Clarke, in one of his science fiction books, wrote an appendix in which he said that this paper paper by Puthoff and H about zero-point energy is the most significant paper that he's ever read, and he wrote an entire novel about the implications of this technology, that it would enable us to build I think if I remember correctly, an elevator that would go from the Earth up to a space station or environment that was in effect circling the entire planet, and the whole thing would be powered by zero-point energy.
I didn't know that Arthur C. Clarke was interested in that. I'll have to look that up. That sounds like fun. So in the parapsychological community, there is always the question of how the interactions at a distance take place. How can these things happen? And one of the concepts that's been toyed with, which I'm sure you're aware of probably more than I, is that in fact these are quantum vacuum fluctuations that are somehow entangled. And there's an entanglement that takes place over distance and over time. And in fact, from a conventional physics point of view right now, that is true. That these fluctuations are entangled. I, as you know, sort of wanted to avoid talking too much about parapsychology with you right now, because people have trouble believing more than one impossible thing at a time. And really, I'm trying to submerge or quietly put aside my parapsychological work in the past, because right now I think what's important to me, and I hope to the scientific community, is getting this zero-point energy technology out. And that's impossible enough by itself.
I totally understand. In fact, not long ago, Garret, I was reading a chat. I think it was on a website called Reddit, and it was about your work and about your papers, and somebody commented to the effect that they didn't find anything wrong with your work, but the fact that you have a history, which I'm really not intending to bring up, but that I think people who look into your background deeply would find that you also had an interest in parapsychology. I hope on another occasion we can talk about that, but their attitude was that they're suspicious of your conventional work, even though you're a professor emeritus in electrical engineering, because of your interest. And the truth is that every person I know of, including Nobel laureates who take an interest in parapsychology, have suffered from that stigma.
Yes. And this really teaches us that whatever it is we're looking at, whatever outlandish claim somebody might be making, take a look at that claim. Take a look at the evidence. Let's be evidence-based and not worry about painting somebody with broad brushes because we agree or disagree with one particular thing that they may have done.
Well, earlier I referred to Arthur C. Clarke. He was no friend of parapsychology, even though some of his novels were very vivid descriptions of paranormal events. But he himself was antagonistic to the field, and yet he, well, two things. He strongly promoted this paper by Puthoff and H, but even more than that, he created a vivid picture of what the future could be like if this energy were harnessed.
Interesting. You know, I appreciate inconsistency in people. Just because our worldview accepts one particular perspective, if we have something that's inconsistent with it and we accept that too, that to me, that's a sign of wisdom, that we don't have to be fixated on everything we understand being consistent. There's too much in this world for us to understand it all at this point or to have a consistent picture.
Well, I would like to go into, in a little more depth, what the promise of this technology would be, if it could be scaled up and harnessed. For example, we might have automobiles or airplanes that could be powered by zero-point energy.
Imagine that we had a battery that just doesn't run out. And this could be, on a small scale, a little battery that runs our cell phone, so we don't need to charge our cell phones. It could be, on a larger scale, a light that burns indefinitely that we don't need to recharge. It could be, as you're suggesting, it could be cars, electric cars, where recharging the cars is no longer a problem because they're trickle charged all the time from these zero-point energy cells. It could be airplanes that likewise are being charged by zero-point energy. Imagine a world in which we're not constantly being buzzed by planes overhead because the engines are completely quiet. They're electric engines. Or you go a step farther. We have power lines everywhere so that we've got central power sources that drive everything in our house from some remote either solar field or coal-fired power plant or something like that. Imagine if we just generate everything we want locally, so we don't need an infrastructure. We don't need a power infrastructure. Everything is local. It could be so local that your toaster doesn't plug in anymore. Your toaster has its own power source. So once you start thinking about the implications of this, they're tremendous. The implications also are tremendous if we're talking about fuel. And clearly, we are burning too much carbon-based fuels. It's ruining our world on multiple levels, from acidification of the ocean to all sorts of other issues. And I'm not going to even get into climate change, although that certainly is something that we can talk about. And so if we are changing the whole energy infrastructure in the world, it makes our local lives cleaner. It makes us more independent. It probably changes geopolitical alliances as well, if everybody produces their own power. So the implications are huge. I'm hoping that they're more positive than negative, but I don't think it's hard to think through some negative implications of just everybody having more power than they need.
I wonder if we're extracting this power from this free energy source, would that create heat in our environment, for example?
It would. However, this has actually been calculated, and the amount of heat that we would be producing, at least if everything that we now power were converted to this sort of energy source, would be small compared with what's coming to the Earth from sunlight or from internal thermal generations inside the Earth. So that's not a significant problem yet.
Let me ask you this. Suppose you were, instead of an inventor of this technology, you were an investor yourself. What would be your major concern, the biggest potential problem that you would see if you were endeavoring to invest in Garret Moddel?
I'm not a deep thinker in these domains, so let me give you some shallow thoughts. We have, for eons, had public speakers and public music performances, and they were in the Colosseum in Rome, or in these great concert halls that we had built in Europe over many centuries, and it worked very well. Then we developed public address systems and had amplifiers and microphones. And so at that point, you could perform as loudly as you wanted without having to worry about the acoustics that you were in. And so now we're in a world where everything is too loud. We have this infinite capacity for making noise, and we make too much of it. Similarly, for years, in the winter it was cold indoors and we wore more clothes, and in the summer it was warmer. Now we have air conditioning and heating, and so we over air condition places. So if you go into, in the middle of the summer, into my office here at the university, they over air conditioned it and I have to put on these heavy sweaters. So these are shallow examples of overuse of a technology. I'm sure there are much deeper ones related to war and strife and power balance. But perhaps you have more insights than I on that.
Well, if I were an investor, I would be less concerned with the overuse of the technology than with the potential that it might not work at all. So that's really what I was sort of driving at with the question.
Yes, that certainly is a risk. And that's a risk that an investor faces with almost any new technology. There's market risk and there's then technology risk. In this case, there's virtually no market risk because if we're getting it to work on a large scale, there will be a market for it. And so there is only the technology risk.
A battery that is always producing energy would seem to be a no-brainer.
Right. Absolutely.
So I guess we get back to maybe the criticisms of people who would say, well, you're violating the second law of thermodynamics, therefore something must be wrong.
Yes, I think so. And, for most inventions that go out into industry and are adapted, you're not having to convince people that the fundamental physics is correct. Usually an investor just wants to see, did you build a widget that works? In our case, we have to do two things. We have to build that widget that works, which we've done so far on a small scale, and you've got to convince them that the physics is right. And so really, my lab is working on both of these levels.
Well, I'm reminded of my own mentor. I was very blessed when I was a graduate student to be taken under the wing of Arthur M. Young, the man who invented the helicopter, the first commercially licensed helicopter, the Bell Model 47. And he had a barn in Pennsylvania, and he worked on basically toy scale models about this large. And he got a small model like this that would hover in midair, and he was able to take it to the Bell Aircraft Corporation, and it took them a few years, but they built a large-scale model, and today the world is full of helicopters as a result of that. So you might very well be in a comparable position.
Interesting. So how has that affected your approach to what you do?
Well, I've done monologues about Arthur M. Young. He had an enormous influence on me. He was really a cosmologist. He said that he wanted to prove that he could invent something like a helicopter in order to be worthy of being a philosopher. He felt that the problem with philosophy was that it hadn't taken into account all of the marvels of technology and how they're affecting our lives. And these days, if you couldn't demonstrate your worth as a master of technology, you shouldn't be doing philosophy.
Mm-hmm. Very nice.
Yeah. So I applaud you and the work you're doing. Of course, we won't know the final outcome until you have a chance to really scale it up, and I hope you do. And for all I know, maybe this interview will help in that direction. It doesn't seem to me, I don't know how much money you're looking for, but it doesn't seem to me in today's world, given the promise of the technology that you've been working on for so long, that it should be impossible to keep on developing your invention.
No, I think it should be quite feasible. I've worked on technologies before in which I've raised a good bit more money than we're needing for this technology. It's just they were ones that were clearly believable, and so the issue here is that an investor or a partner needs to not only have the resources available, but also has to have the commitment that it's worth taking the risk.
Well, Garret, Moddel, this has been a wonderful discussion. It's a real pleasure for me to connect with you. I might point out for the benefit of our viewers that we first were able to meet face-to-face a number of weeks ago at a meeting of the Society for Scientific Exploration. And it's a wonderful organization that you've been involved in that looks at a wide range of scientific findings that seem to buck conventional thinking.
Absolutely. In my case, if it weren't for the Society for Scientific Exploration, I wouldn't even be working in this field at all. It's simply from the cross-pollination of working with different sort of maverick scientists that I ended up here. So absolutely, I recommend the SSE to anybody who's looking for a really fascinating venue for new science.
And we'll post their website in the description to this video. Garret, thank you so much for being with me today.
Thank you. Thank you for having me. I appreciate it.
It's been a pleasure. And for those of you listening or watching, thank you for being with us. You are the reason that we are here. I imagine that by now, many of you already realize that in conjunction with White Crow Books, we've just launched the new Thinking Aloud Dialogues book imprint, and our first title is There Life After Death? New Thinking Aloud is a non-profit endeavor. Your contributions to the New Thinking Aloud Foundation make a meaningful difference in our ability to produce new videos.